Welcome back, folks. For 3 of the structures we drew, pardon the typo here, I fixed it on this, you can fix it on yours, we had multiple ways we could have decided to draw the structure and still achieve octets for every atom. And so we're going to take a moment to draw all the options that we had. For instance, with the carbonate, we needed to put in 1 double bond, but that double bond could have gone to any of the 3 oxygen atoms that we like. Of course, in this case here, I would have had 2 pairs of electrons on the bottom oxygen. On this one, I would have 2 on the left side oxygen. But any of those would have been perfectly viable ways to draw carbonate structure. By the same token, we mentioned as we were doing these two that we had the option of either putting double bonds on both sides or a triple bond on one side and a single on the other. Well, let's go ahead and fill in the other possibilities. So there are possibilities for the NO2 plus ion, and similarly over here, we could put the triple bond to the nitrogen, or we could put double bonds on either side. Now, what we're observing here is a phenomenon known as resonance. And so we would say that these structures for the carbonate ion, this group right here, or these structures here, are a group of resonance structures. Apparently that line needs to be longer. Now, to be a good resonance structure of another structure, so for instance, for these 3 to all be considered good resonance structures, there are a couple of conditions that have to be met. Namely, to be a good resonance structure, a diagram must have all of the nuclei in the same place and only the electrons moving around. So for example, it wouldn't be a resonance structure of this if I suddenly put an oxygen in the center and moved the nitrogen to the outside, or if I just took this structure and flipped the whole thing 180 degrees. It wouldn't be considered a resonance structure. I know that with carbonate, it kind of looks like something that maybe I'm just rotating over and over again, but from at least the point of view of what we're thinking of as we do it, we're considering this to be these nuclei all stuck in place and the electrons simply being moved around. Of course, they also need to satisfy all the other conditions that make a good Lewis structure, right number of total electrons, octets around everything. Now, when I have a set of resonance structures, one big question that comes to mind is, how do I know which of them is the best representation of how this molecule is really built? To answer that question, we're going to appeal to something known as bonding preference. And in order to get a sense of how bonding preference works, I'm going to return to our original Lewis structures from earlier. Notice when we worked these out 2 videos ago that in each case, if I look at the number of bonds that an individual atom has formed to it, it is the same as the number of electrons that it needed to complete its octet. So these chlorines, these bromines, these fluorines, that chlorine, and this hydrogen for that matter, all needed 1 more valence electron to complete their octet. And so each of them has 1 bond to it. On the other hand, the oxygen needed 2 bonds because it needed 2 electrons. The phosphorus up here is in group 5. It needed 3 new electrons. It formed 3 bonds. We can even see it with some of the ones that did double bonds earlier. If I look specifically at formaldehyde here, notice the hydrogens needed 1 each. They form 1 bond. Oxygen up here needed 2 bonds in order to get its 2 electrons, and the carbon needed 4 bonds to get the 4 electrons it needed, being in group 4A, to reach an octet. Phosphorus looks just like nitrogen did, and in fact, if you recall oxygen, which we looked at earlier as well, we looked at all of these here, these diatomics, and notice that nitrogen in group 5 needs 3 electrons, phosphorus in group 5 needs 3 electrons, oxygen in group 6 needs 2 electrons, and notice how we have a triple, and a double bond respectively. Now, I do want to call your attention to carbon monoxide, because this is the proof in the pudding, as it were, that it's not an ironclad rule. the first thing that matters when making Lewis structures is you have to form octets with the right number of total electrons. Well, for carbon monoxide, there is no other way to do this besides that. And so there's no point to ranking structures or trying to mess with bonding preference because I only had one choice. On these, I do have options. So what we're going to do is look at those resonance structures and ask ourselves which ones do the best job of matching the bonding preferences. So we'll start with carbonate. Bear in mind that carbon should have 4 bonds to it because it is in group 4 and needs 4 electrons. And if I look at each of these, I will see 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. So in every one of these, carbon is happy, which is actually unhappy for us because that means it doesn't help break the tie. Now, if I look at any of the oxygens, there are 2 possibilities. Either it's in a single bond or it's in a double bond. Well, if it's in a double bond, it has the usual 2 bonds. So that oxygen is happy based on bonding preference. The single bound oxygens would appear not to be happy. However, notice that in each case I have 2 happy atoms, the carbon and an oxygen, and 2 unhappy atoms, the other 2 oxygens. What that tells me is that these 3 structures are all equally good. And in fact, the best structure for carbonate isn't any one of these individually. It's instead an average of all 3 of them. And so your book will show you how to draw what's called a resonance hybrid for something like this. And essentially what we would do is say that all of these are at least bound singly, but that double bond is being shared among all 3 oxygen atoms. And then I'll just draw the 2 lone pairs on each oxygen that happen to belong to the oxygen no matter what. And we can draw it like this. The basic idea being that all of these bonds and all of those oxygens are in fact the same as each other. There's not a special one that's in a double bond because the best structure is an average or hybrid of the 3. Now that's only the case if all structures are equally valid. Let's try this for the other 2 ions. For our NO2+, in this case here, notice that nitrogen, no matter what, has 4 bonds to it, either a triple on one side and a single on the other, or 2 doubles. Nitrogen, though, we said, is in group 5, so nitrogen wants 3 new bonds, therefore none of the nitrogens are happy. But again, doesn't break a tie for us. On the other hand, we said oxygen wants 2, so notice how in these 2 structures, neither O is happy. Single bond, triple bond, no good. But in this structure, both O's are happy. And so NO2+ isn't going to appear as a resonance hybrid. That is the structure that best represents NO2+. I'm going to call your attention to one other thing about these structures. You'll notice that because these are ions, no matter what we do, one atom is going to be unhappy, at least. And the reason for that is that there's at least one atom that is going to act like it's in a different group, because something had to either lose or gain those other electrons. If you think about this one for a moment, nitrogen with its 4 bonds is kind of acting like a carbon. Well, a carbon is a lot like a nitrogen, but with 1 fewer electron. So you might say to yourself, the nitrogen here is the thing that's lost the electron in order to make this a cation. On the other hand, these O's, the ones we said were unhappy, have 1 bond. So they're acting like halogens. They're acting like they're in group 7, which is what you would expect an O to do if it picked up 1 electron from somewhere else, maybe from a metal ion that it's bound to. And so you can look at this as being these 2 electrons living on that oxygen and that oxygen. I bring this up because we're going to need a little help on this one in a moment. Let's go down the line and decide which atoms are happy and which ones aren't. I'd like you to pause the video and try that for yourself. Okay, after you've taken the time, I hope you determined that all 3 structures have happy carbons, because carbon wants 4 bonds, and it's either got a triple and a single, or 2 doubles. On the other hand, only one structure makes the nitrogen happy, and only one structure makes the oxygen happy. Nitrogen wants 3 bonds, so unhappy here, unhappy there. Oxygen wants 2 bonds, so unhappy, unhappy, happy. So unlike the situation here, this is actually the worst possible structure, the one that we drew initially for this cyanate ion. So we'll cross that one out completely, just like we could have done on those. These two, on the other hand, are equally good from this perspective. What I could say, however, is that one of these has the extra electron on oxygen. That's why it's the unhappy atom, because it's acting like a halogen. It's only got 1 bond. I could also say that this structure here has the extra electron on the nitrogen, because now the nitrogen is acting like group 6. It's acting like O, as if it had 1 more electron on it. And so now the question is, where is that extra electron more likely to perch? And the answer to that question lies in something called electronegativity, which we're going to use both for this purpose and to determine which covalent bonds are polar on our final video for this module.